Hello everyone, I'm Wong Tianjun from Sun Yat-sen University. Today I will talk about our research, Kmon, an in-kernel transparent monitoring system for microservice systems with eBPF. Since the advantage of microservice in agility, efficiency, and scaling, it has become the most popular architecture in the industry. However, as the increase of microservice complexity and scale, it becomes challenging to monitor such a large number of microservices. Some monitoring tools for microservice can collect and aggregate indicators. However, most of them only focus on basic metrics of resource usage, and sometimes need to change the underlying infrastructure. Some tools can capture the internal indicators, such as S-trace, but they sacrifice the performance of systems and cannot well-fit microservice environment. Our monitoring system, Kmon, can capture conventional metrics more accurately. Furthermore, it can collect fine-grained internal performance indicators, such as the number of system calls. Internal indicators are useful because they can reflect some hidden problem like life log. Indeed, current microservice monitoring tools are almost impossible to find out these deeper problems since they cannot obtain internal events. Kmon can do it thanks to eBPF, a technology that can run sandbox programs into Linux kernel without changing kernel source code or loading a code module. eBPF can be attached to a trace point and a kernel probe to observe kernel runtime behavior and extract visibility data. It can also collect and aggregate customer metrics in kernel efficiently and safely. The basic architecture and the procedure of eBPF shown in the picture. The object file of eBPF program is loaded to in-kernel with some trace point or probe attached. The verifier checks the eBPF program to ensure it cannot damage the Linux kernel. After passing the check, JIT transfers the bytecode of the eBPF program into machine code. When trace point or probe triggered, eBP program runs collected and aggregate metrics in kernel and store them into eBPF maps. With the help of eBPF maps to communicate with other user space programs, eBPF programs can monitor in a flexible way. There are some challenges to use eBPF to build microservice monitoring tools. One challenge is that metrics aggregated by eBPF are still at a low level. They are easy to understand if numeral, such as function execute count or CPU usage, but they are human unreadable if there are no numerical data. For example, the execution stack includes multiple function address data, which are hard to understand without address table, so it needs to be translated after extracted. Another challenge is that the initial eBPF is used at the kernel level, so it is hard to capture high-level information, such as microservice information and user-defined configuration. While in a microservice systems, the target monitored changes are common as containers usually update frequently. So, a monitoring system should enable eBPF to notice the change of microservice. To handle these challenges, Kmon brings in a provider component to collect high-level information, like the change of microservice and necessary data for translate unreadable data. The collector, which load and control eBPF program behavior, using this information to pass in-kernel data extracted by eBPF program to human-readable indicators and notify eBPF program to change their monitor target. All indicators translated by collector can export to database by exporter. The next part, I will talk about more detail of each part of Kmon. First is the provider. Provider is responsible for collecting high-level information to collect information that are hard for eBPF program to gain. There are three types of information that provider should to collect: user-defined configuration, microservice, and host environment. User-defined configuration decides which indicator should be monitored for microservice, the detail level of monitoring, and where the data should be exported. Provider watch all changes of configuration, and Kmon can dynamically change its strategy by this information It is useful as some indicator like off-CPU time contains excessively information, which cause more CPU and memory usage. System operator or some automatically algorithm can disable it or set it to a low detail level in Kmon, enable it with high detail level when abnormal occurred to gain more information for debugging, which can reduce the average overhead of Kmon. Microservice information is for eBPF program to decide monitoring target. eBPF cannot identify the container directly. It needs PID of process running in microservice. So provider collect them by the microservice API and keep updating them to see the microservice frequently changes. Host environment information is for collector to translate data from eBPF program into a human-readable format. What kind of information needs to collect is depend on the type of monitoring indicators. For example, the output of set trace is a sequence of address related to the kernel function. The collector needs the address table to find out which function of each address represents. Second is the collector interact with eBPF programs. It looks the eBPF program into kernel and communicate with eBPF program via eBPF maps. Communication contains two parts: to control behavior of eBPF programs and to receive data collected by eBPF program. For the former, collectors analyze high-level changes from the provider. For example, if services are deleted or created, collectors should immediately notify the eBPF program. Similarly, if the configuration is changed, relative collectors need to apply these changes to control maps. For the latter, controller receives data from data maps. These raw data are usually human unreadable, so collectors should translate them using information provided by provider. Both data map and the control map is eBPF maps. It's not the eBPF conception, but Kmon itself. To make Kmon a flexible system, eBPF program need to adjust their behavior when microservice or configuration changes. Kmon adjusts it by storing the control messages into eBPF maps. eBPF program checks maps from choosing executive branch. The usage of these eBPF maps is different from eBPF maps that store collected data. Therefore, the former called control maps and the latter called data maps. Kmon can collect various types of indicator via its architecture. There are too many types to decide which should be focused on when monitoring, so a hierarchy of these indicators for locating the problem is helpful. The first is TCP request level. TCP request is common in microservice, and many abnormal detecting algorithms for microservice depend on it. In this level, Kmon captures indicators of each TCP connection, such as quaternion and latency. The second level is the topology level. Dynamic service graphs are formatted by TCP request data. Nodes in the graph represent the service instance, and the link between nodes reflects flow of recent network requests. The aggregate information of each host from the whole microservice system. Data at this level is iterative of human and algorithm to identify the relation between services. According to the latency from information and the topology, it is convenient for system operators to estimate if there is an abnormal node in the graph. The third level contains other fine-grained indicators for further investigation. They include metrics relative to CPU, memory, block I/O, and some others. The source code of eBPF programs for Kmon refers to DCC examples, with some changes to match Kmon's architectures. Here is an example of collecting indicators of TCP request. Table shows what should be provided by provider and what kernel function should eBPF program to be attached. The request latency is calculated by subtracting the first received message timestamp from the last sending message timestamp. So eBPF should hook relative function code to capture the time. Kmon only collects the requests sent to servers, but it is difficult to distinguish the direction after a socket being accepted. Kmon used the hook about accept and close operation to decide short connection directions, which assume that the server side executes the accept this call. After that, service topology can be constructed from TCP request. Other indicators share the same architecture of Kmon, but with different eBPF programs and collectors. Tables show the information about some implemented indicator that the provider and the eBPF program collect. And the pictures show the visualization of those indicators from translated in-kernel data. Our experiment used 4 Linux virtual machines with Linux kernel version 5.4 to make our Kubernetes cluster. We used Hipster Shop, a cloud-native microservice application demo for Google as benchmark. The first experiment, a Kmon node is run in a host, which exporter is disabled, so we can focus on the indicator monitoring performance. The CPU usage is negligible. Then we deployed Kmon node in each Kubernetes node with all indicators monitoring enabled. Table shows the inference in response time is also negligible. Both experiments show that the memory usage is relatively high. It is possible to optimize, and we will optimize it in the future. Here is the conclusion. To create a transparent monitoring system with 5 gram indicators, we introduced Kmon and eBPF-based systems. They transparently captured various types of indicators and organized them in 3 levels, which is convenient for system operators and algorithms. Experiments showed it has low CPU usage and little influence on server's response time. In the future, we aim to find a better way to capture TCP connection information on fewer assumptions. The current assumption of TCP request is not suitable for some specific type of service like messaging queue. The memory usage of Kmon also needs to be reduced. 2 directions are considered. One is to use library libBPF instead of libBCC, which use less memory in runtime. The other is to find a better representation of indicators to compress their size. That's all. Thanks.